Okay, so thanks very much for the presentation, and let me thank the organizers of this workshop. And it's a pleasure to be here, even though, as my colleagues said already, it would have been a much greater pleasure to be there in presence. But let's hope for a next edition of the workshop in full presence. So I want to present you this result about the prescribing curvature equation. This is a result in collaboration with Giovanni Comi at the University of Pisa. Okay. So let me start with the equation. So I fix an open bounded and set omega with the Lipschitz boundary, and I consider a measure mu, which is a signed and finite Borel or Radon measure on omega. So this is the kind of equation that I want to consider. So it's the equation which is very well known in some maybe more classical settings. And indeed, we have this classical setting when the right-hand side, the measure mu, is actually associated with a Lipschitz function h, so it's just h times the Lebesgue measure. And this equation is very important. It's a classical equation in classical PDE, and it is physically motivated by capillarity theory. We have already seen it in previous talks, and in particular when mu is 0, we have the minimal surface equation. So it's an important equation, and for which some existence and regularity results are, say, well known, at least for the classical situations. And these results, so a consistent bunch of results for this equation have been obtained in between, say, the 60s and the 90s. However, in the case when mu is a more general measure, in particular when it has a non-trivial singular part, so even just the existence is an open issue. So this is the issue that we want to face. So the first goal, number one, is to define an appropriate notion of weak solution for this equation and for suitable measures, a suitable class of measures. And then goal number two, to prove existence of weak solutions. Okay, so this is just a small list of references that I put here because I wanted to tell you that there is one of these references, this one by Enrico Giusti, which is my preferred reference for the topic I'm going to present. So this is an important paper by Giusti on the equation of surfaces of prescribed mean curvature, existence, and uniqueness without boundary conditions. So here you can find, say, the classical results that I am referring to which I am comparing the new results that I will present. So let's now look for necessary conditions, or natural necessary conditions for existence of solutions. So assume that we have a solution and assume that this solution is smooth enough, and then we do some calculation. So if we do that, we assume that the solution exists, then we, just for convenience, we set Tu as the gradient of u divided by the square root of 1 plus modulus of grad u squared. So this normalized gradient. And then we integrate the equation, both sides of the equation, on a smooth subset A of omega. And what we get is that the right-hand side, so in absolute value, so the measure of A, mu of A in absolute value, is equal by the divergence theorem to the absolute value of the flux of the vector field Tu through the boundary of A. And since the vector field Tu is strictly smaller than 1, because we are assuming that U is a solution, a sufficiently nice solution, then we can bound this absolute value by the Hausdorff Hn-1 measure of the boundary of A, which is say what will be denoted more generally later on as the perimeter of the set A. So this leads to the necessary condition for existence of solutions, this one that you see here. Okay, besides the necessary condition, it is also important to distinguish between two situations, so extremality and non-extremality. What do I mean by that? Always, taking the necessary condition as granted, we say that the measure mu is extremal if when you test, say, the previous inequality by replacing A with the whole domain omega, you get equality. So this is the extremal situation. And on the contrary, we say that mu is non-extremal if instead we get the strict inequality also for the whole domain. So these there are a couple of remarks that should have done that I have to do. First of all, the second condition, non-extremality, is equivalent to this apparently stronger inequality, where L is a suitable, say, uniform constant between 0 and 1. Second remark, the extremal case is not just, say, theoretically interesting, but it is also physically interesting, as it corresponds to the capillarity phenomenon for perfectly wetting or perfectly non-wetting fluids under zero gravity conditions. So it's an important situation. Okay, so let me present a classical result that is inside this paper by Giusti. Assume that omega and H are both Lipschitz, and take, as in the classical situation, the right-hand side mu as basically the function H, so H times the Lebesgue measure. Then the necessary condition turns out to be also sufficient for existence of classical solutions of the prescribing curvature equation. So how the proof works, more or less, very, very roughly. So first of all, one deals with the non-extremal case, which is easier and which is a sort of a variational case. So here one fixes a certain big ball containing the domain omega, and the Dirichlet datum in weak sense, just a function phi in Sobolev space W11 of the whole ball. And then one minimizes this functional, which is the area of the graph of U on B, plus the integral of H times U on omega among the function of the BV functions that agree with the prescribed datum phi on the complement of omega inside B. So this is the technique. And instead, in the extremal case, which is a more delicate case, one finds solutions that are non-variational in general, because they are limits up to translations of sequences of non-extremal solutions that you can obtain by restricting the domain by considering subdomains, so a sequence of subdomains tending to the whole domain. And so by taking this limit up to translations, you can obtain the so-called general solutions of the prescribing curvature equations in the sense of Mario Miranda. Let me get closer to the goal number one, and for that I need to make a premise concerning this notion of area. So what is the area of the graph of a BV function? It's a measure that can be defined in a very much similar way to the definition of the total variation of the distributional gradient of U. And this notion corresponds to the perimeter of the epigraph of the function U evaluated in cylinders, okay, in which you fix the base domain and you take the cross product with the R. It's a notion that, of course, satisfies some relationships, some inequalities involving the total variation. It is a convex functional and lower semicontinuous in L1. So let's see which is this weak the natural weak formulation of this PMCM equation. And to present it, we follow the approach of that you can find in a paper by Scheven and Schmidt, even though in a specific setting. So here, in this paper, they consider super solutions in the BV setting of equations of one Laplace and of minimal surface types. And how to do that? So let's do a formal computation. So assume that our objects are point-wisely defined, that are, say, classical. So we take the renormalized gradient TU and multiply it by du. So by very easy computations, we end up with this representation of this product in terms of what can be recognized as the density of the area of the graph, minus a certain function, which is a function between 0 and 1. And therefore, it seems natural to get a weak formulation from this identity, because this identity is somehow characterizing the vector field TU among a subunit vector field, so vector field whose norm is less or equal than 1. So this identity somehow characterizes T of U, TU, as the renormalized gradient of U. And that's the idea. The idea is to say that U is a weak solution of the PMCM equation if one can find the Borel vector field T such that this T is subunit, its divergence in the distributional sense is mu, and this product T times du is given by this difference of objects that can be both interpreted as measures. So the first is the area of the graph measure, and the second is, say, the measure represented by an L infinity function, which is this function between 0 and 1. But this formulation has some problem, because basically you don't have, it's not clear which is the meaning of this dot product. So this dot product in general does not make sense. For instance, when T is not continuous, and in this setting we do not expect continuous vector fields, so smooth solutions in general, and U is just a BV function. So how to solve this problem? Well, the solution is to use the theory of pairings. between divergence measure vector fields and BV functions. This is a theory that has been initiated by some seminal work by Ancelotti and then developed by various authors later on. But the kind of pairings I will need have been partially introduced in the work by Scheven and Schmidt, and more with more detail and more generality by this last work by Crasta, De Cicco, and Malusa, which is a very recent work. These are called lambda pairing, and we will see which specific lambda pairing will be useful for our purpose. So let's talk about lambda pairing. What is a lambda pairing? And to introduce them, I need to make a few, to introduce some notation related to the decomposition of the distributional gradient of a BV function. So this is a well-known decomposition and into absolutely continuous part and a singular part. And the singular part is further decomposed into jump part and the cantor part. The jump part in particular can be represented in this form where you have, say, the Hausdorff Hn-1 measure restricted to the jump set. And you have a vector density here given by a normal, a properly oriented normal, times the jump that the function u has at a certain point of the jump set. So this jump is just the difference between the two upper u plus and lower u minus traces of the function u at the jump set. So with these objects, in particular the two upper and lower traces, we can define some representative of the function u. And how do we do that? We fix a Borel function, lambda, from omega to 0, 1. And for almost every x, we define a representative of the function u that we call u lambda in this way. So if we are on the jump set, we take the convex combination of u plus and u minus in terms of the function lambda. And if we are not in the jump set, so up to negligible sets, we are outside the discontinuity set as u, we take the approximate limit. Okay, so this is a representative depending on the choice of the function lambda. And note that in the particular case, lambda equal 1/2, we get a more classical representative of the BV function u, which is the u star, the so-called precise representative, which is also the object you obtain when you take almost Hn-1 almost everywhere limits of the convolutions of a BV function locally. So this is the so-called precise representative, which is a special case of the u lambda representative. And then what is a lambda pairing? So you fix your domain, Lipschitz, and a function u in BV, also in L infinity, and consider a vector field in dm infinity omega. So it's an L infinity vector field with whose divergence in distributional divergence is a finite Radon measure, and fix your function lambda as before, and also u lambda. Consider u lambda the representative. Then, what is the pairing? This object here, xi, du sub lambda. So this is the pairing, and it is defined as the difference of these two distributions. So the divergence of u times xi minus u lambda times the divergence of xi. Why this distribution is actually a measure? So these two guys here are measures. Well, because the divergence of xi, since xi is a Radon measure, and it is a divergence, so automatically it must be absolutely continuous with respect to the Hausdorff measure Hn minus 1. So that's why it's correct to multiply u lambda, which is defined Hn minus 1 almost everywhere, times the divergence. Moreover, by this pairing, you can prove a generalized Gauss-Green formula. So there is a generalized Gaussian formula involving various weak objects. I am not going into details here, but this is just to say that the pairing allows us to use Gauss-Green. Okay, so let's come to the weak definition, the correct weak notion of a solution to the PMCM equation. For doing that, we need to consider the Hahn partition associated to the measure mu. So the Borel partition of omega into omega plus, omega minus, such that when you restrict mu to, say, omega plus or omega minus, then you get the positive part or the negative part of the measure mu. Then we say that U is a weak solution to the PMCM equation if, same thing as before, but now we have the correct meaning of and the correct pairing that we should consider here between the vector field T and the gradient du. So this is a special pairing given by the Borel function lambda mu, which is nothing but the characteristic function of omega minus, so of the portion of the domain where the measure is negative, the measure mu is negative. So this is the correct pairing in order to get also the next results that are existence results. Note that in this case, the function u lambda mu, so the representative corresponding to this specific choice of lambda, is nothing but the function u plus on omega minus intersection with ju, and u minus on omega plus intersection with ju. And outside the jump set, essentially, we have the continuous, the approximate limit u tilde. Fine. So we have a formulation, but the big problem here is to prove existence of solutions. And indeed, our choices will be such that the existence will be guaranteed. So we say that we need some assumptions, of course, on the measure mu, and what we require is that mu is admissible. This means that mu essentially belongs to the dual of the space BV. I say essentially because then there are some extra hypotheses that probably are just technical. We are not sure that they are needed, but for the moment, our technique requires some extra assumptions. So we need some properties of the singular part of the measure mu. Basically, it must be supported on some sets, gamma plus, gamma minus, the two positive and negative singular parts. These must have a finite Hn minus 1 measure, and they must be separated, so their intersection must be empty. So if we have this admissibility hypothesis, this is the result we can prove. So this is our main theorem. So assume that mu is admissible and non-extremal. Then there exist weak solutions to the PMCM equation. So how do we do? So let me give you a few highlights in the remaining time. I think I have maybe around 5 minutes or maybe a slight more.
A little more than that even.
Even more, okay. But I will try to stay, not to be too long. So how do we do that? We follow a variational approach. And as before, we fix a ball, a larger ball containing the domain and the Dirichlet, kind of weak Dirichlet datum phi. And then we consider the variational problem formally as before. But here we use the lambda mu representative. Why this is so natural here? Well, because the lambda mu representative is the one which allows to minimize, is the optimal, say, representative of the PV function u in order to minimize this integral. So it is natural from the variational point of view to consider the function lambda mu as I introduced before. Okay, and then one tries to apply the direct methods of calculus of variation, so to prove lower semi-continuity and compactness. But unlike the classical case, this point, this lower semi-continuity in particular, and also compactness, they are no more as easy as in the classical case. They are far from being as easy as in the classical case. So I cannot enter too much into the details, but I want to just to say something about a tool that we had to use for the proof of lower semi-continuity in particular. But this tool is also useful also for compactness and more generally for the study of pairings, of lambda pairings. But we will see later on. So let me say something more about the issue of lower semi-continuity. Why this issue is so delicate now? Because we have that the first term of the functional that we want to minimize is lower semi-continuous. This is the area of the graph on BV. So no problem with this term. So the problems come with the second term, the integral term. And this is, in general, it is not lower semi-continuous unless the singular part of the measure is zero. So, but we want to consider singular measures also. And so let me draw some picture, very elementary one-dimensional picture to show you why there is a lack of lower semi-continuity here. So consider, for instance, a sequence of functions like those for a measure mu, which is nothing but a Dirac delta centered at the origin, say. So assume that these are the graphs of your function, and the sequence proceeds like this. Okay, so you can imagine what happens when h goes to infinity. So for all the elements of the sequence, so the value at the origin, so the sequence is a sequence of continuous functions. So the integral here is zero. But when you pass to the limit, you get this limit function, and the lower trace of the function u, which is the one that should be paired with the measure mu, is no more zero. And so you have a jump upwards and a loss of lower semi-continuity. Okay, this is a problem, and you might imagine that in more general situations it's a maybe harder problem. But here you see some kind of paradigmatic situation. And indeed, if you look at this simplified picture, you might see that the bad behavior of the integral term happens when, at the same time, you have a drop down due to the strict lower semi-continuities of the area term. So local failure of lower semi-continuity of the integral term should be possibly compensated by a failure of continuity of the area term. And this is exactly what happens, also relying on the non-extremality assumption, which basically can be used in this simplified way form, combined with the coarea and layer cake formula. But this is it is not so easy to prove this in the general case. It's quite technical. And indeed, I was saying before that there is a nice tool that we can use, and we had to introduce before this proof of lower semi-continuity. This tool is a refined form of the Ancelotti-Giaquinta theorem. So let me present this result. We call it lambda approximation. It says that if you have a BV function, u, and you fix your function lambda, then you can find a sequence of smooth functions such that the sequence behaves like the classical Ancelotti-Giaquinta approximation theorem. So it converges to U in L1. The total variation converges to the total variation of the limit. And let me also add that the area graph measures converge, so that the total area of the graph converges to the total area of the limit. But this is really the new point, an important point. We have that UH converges to U lambda Hn minus 1 almost everywhere on omega. So we can force a specific convergence Hn minus 1 almost everywhere to the function U lambda, to the representative U lambda. And the idea is, again, through a very simplified picture, is to start from the classical result to the fact that, and recalling that in the classical result, one reconstruct convergence to the precise representative U star, but then there is a problem of perturbing the object that you get by convolving typically the function U. You have to perturb it, and in order to approximate U lambda, so your generic, say, convex combination of U minus and U plus in terms of lambda. So this is the rough idea of what should be done. There is a perturbation of the classical Ancelotti-Giaquinta sequence. Then we have compactness, and then I'm getting, I think, to the end. Compactness is obtained by showing a first estimate in which we use lambda approximation combined with co-area formula. And then from this estimate, it is not difficult to get an estimate for the zero extension of U outside the omega, for the total variation of this zero extension in terms of the functional and of the data of the problem, so that we get compactness just by using Poincare inequality. So this is how compactness works. I think I'm running out of time, so I just wanted to conclude by saying that in order to prove that once you have a minimizer U tilde, say, of the functional J of mu, in order to show that this minimizer is a weak solution of the PMCM equation, there is an argument relying on convex duality that one should put into place. And the argument is mostly classical up to some points, so up to some choices that one has to do in a specific way in order to sort of define the correct spaces that have to be used in this duality argument. But I think that I am out of time, so I would stop here. And if you want more details about this last part, I can maybe go on and tell you more. So let me go at the end. Thanks you for your attention.
Thanks very much for your presentation, and thanks for leaving a little bit of time for questions. Is there a question that we need to answer right now? Yes, please just speak up.
Yeah, hello. So thanks for the talk. So can you show your technical assumption on the mu?
Yes, let me go back. Sorry, I went too fast. So the admissibility.
Yeah. So does it imply already that there is no counterpart, I think, or it's only a jump?
Well, no, not necessarily, because I'm not assuming that the gamma plus and gamma minus are rectifiable, for instance.
Oh, right. Okay.
No,
I see.
I just ask that they have Hn minus 1 finite measure. So but yeah, Yes. So so in general, I think maybe I have simplified a little bit the assumptions here. We can also consider a counterpart, actually. So it is the part which gives, say, a non-trivial term which is absolutely continuous with respect to Hn-1, but with a non-trivial density that must be actually supported this way. And so I have a bit simplified this assumption here for the presentation. But you're right. There is also.
But you can have counterpart in principle.
You can have. You can have counterpart. Sure.
Okay. Thank you.
And indeed, let me add a thing. So the counterpart is not it's not a big deal, not a big problem, because it does not interact with the jump part of the solution U. So the problem is when the jumps of U interact with the singular part of mu, and the counterpart does not interact really, because it's it's a measure that is not visible by Hn-1. I don't know if I have answered your question.
Yeah, thank you very much.
Okay.